Alright, let's see if I can actually do the stream right. Okay, today is going to be a hard one that I previously solved with no actual memory. Minimum total distance traveled. There are robots and factories, x-axis. On the x-axis, the robots have positions in an array. Their factories have an array that is their positions and a limit, where the limit is the number of robots that they can repair. The positions of each robot are unique. The positions of the factories are unique. Note that a robot can be in the same position as a factory. All the robots are initially broken. They can keep moving. They keep moving in one direction. The direction can be negative or positive. When a robot reaches a factory that did not reach its limit, the factory repairs the robot and stops moving. At any moment, you can set the initial direction of moving for some robot at any moment. So in theory, you could not do it at the start, but I don't see why you do that. Your target is to minimize. Yeah, I don't see why you do. Your target is to minimize the total distance traveled by all robots. Return the minimum total distance traveled by all robots. The test case is generated such that all robots can be repaired. All robots move at the same speed. Two robots move in the same direction. They will never collide. Two robots move in the opposite direction and they meet at some point. They do not collide. They cross over each other. If a robot passes a factory without reaching its limit, it crosses it as if it did not exist. If the robot moved to a position from position X to position Y, the distance it moved is Y minus X. Okay, and then here the positions of the robots are such. The factory 2 can repair 2, the factory 6 can repair 2. In theory, I think you could also move this robot to this factory as well, but that'd be still forward movement. This thing doesn't move. And then this one is just moving 1 each, so it's 2 total. Alright, and then there's going to be up to 100 robots in factories. The positions are pretty much any number, any integer. And the maximum kind of repairable amount of robots for a given factory can be 0. Alright, that's troll. 0 or up to the number of robots. That is pretty troll. Your input will be generated such that it's always possible. So anyways, I did reread this and I think I need to sort. I just don't see that, like, if you don't sort, then in theory you can maybe open yourself to linear time complexity solutions. But I doubt that you can actually do a linear one here. It's a little too complicated with that. Linear one you have to do like somehow on inspection of the robot, you can immediately determine what the best movement is for it, and then add that movement to their running calculation. What can you do here? Can you do a heap? So for every robot, you kind of need to know for each robot how close the next factory is. For each robot, how close the next factory is. Can you do that? For each robot, the closest factory, and then move to it. The closest available factory and move to it. So if I somehow had this robot and said that the distance to the nearest left factory that's open is here, and the nearest right factory that's open is here. And then I guess if they're equidistant, then I just randomly pick which factory to go to. That's not going to be correct if for instance, like let's say there's only one repairable robot at this factory, and this one picks this one, so therefore this one has to go all the way here. That doesn't work out. Guess you'd always want to start with a robot repairing at the factory that it's located on if possible. I'm not sure if I need to handle that case specifically to maybe simplify the problem or just allow that case to be resolved in the kind of general solutions. So maybe after I remove all the robots that are on factories, and maybe remove all the factories that have zero repairable, then I would need to greedy approach might not work, right? The greedy approach might not work because you might be greedy in the wrong direction. You might be greedy in the wrong direction. Minimum total distance traveled by all robots. So this robot goes here. I guess you could start by doing maybe if a robot only has one nearest factory, then they have to go to that factory. So you can maybe prune the decision tree there. So let's think about the ends. So let's say there's like a factory at 1,000, or let's say there's a factory at -1,000, and there's a robot at, let's say, -100, and another factory at 0. Would it ever make sense to have the robot that's close to 0 go to the -1,000? Go the non-greedy approach of the nearest. So I guess if this was a 0, well, let's say this was like a 10 here. So the 10 should ideally go to 0, and the -100 should go to -1,000. But then if I do -100 goes to 0, then the 10 has to go all the way to -1,000. I think maybe, I think if any robot ever crosses each other or crosses their movement somehow, then they moved in the wrong direction. Like they should never move over each other, because that means that there was a better way of assigning movement to lower it. Right, so like a -1,000, -100 goes to 0 and 10 goes to -1,000 somehow. Yeah, that crossover is bad. That crossover should never take place. Then that's not guarantee that you would get this. Just having no crossovers is obviously not a guarantee that you would get the ideal solution. Because obviously, if it's just something like this, like -100 to -1,000 is, or -100 to 0 is no crossover there, but there's one that's strictly better. Do 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 do. I solved this before, huh? Generally, when I solved before, I was doing a course on DSA, and I kind of knew what topic it was, so I was solving it without that sort of. I wouldn't even call that a hint. That's really like a big flag as to what the freak you're supposed to be doing. Like, it's kind of a very different order of operation or different order of difficulty than solving it without knowing. Although, again, I think this is probably n log n. I just need to figure out, or I mean, it could be some form of dp, which is generally n squared, or n to some dimension. Yeah, it could be dynamic programming. Feels like it probably should be sorting though. Let's see, if it was dynamic programming, then maybe the state is the index of the robot and whether or not the last robot went left or right. Whether or not the last robot went left or right. Could that work? I mean, I think it might work. Trying to figure out how the index of the robot, whether or not the robot went left or right. And then the current robot needs to figure out how much it costs for it to get repaired. Right, T-O. And if it went left or right, then maybe the position of the latest factory, position of the leftmost factory next to the current robot, the leftmost factory that has a repair shop. Huh, I think maybe that might work. That's an idea. So the state inputs is going to be the index of the robot, and maybe I just need to know the position of the leftmost available factory. Not leftmost, it's the nearest left. I wonder. And then state output would be just the number of the total distance, the minimum total distance up to the state. Wonder if there's a better way of doing this. It is kind of complicated because if you have some robots that, let's say, choose to pick, so you're iterating over the indices of the robots, and let's say somehow you're trying to have the robots pick factories to their right, and then you get to a point where the robots have no more rightwards factories, and now they're choosing factories to their left. And at some point, if they choose a factory to the left that isn't available, then it's not, they must have done something wrong. because the ideal that if there was, let's say, robots at, let's say the capital letters are the robots here. So if I have robot A, robot B, robot C, and there's a factory here that can handle 4. Let's say there's a factory over here that can handle 2, a factory here that can handle 4. Probably shouldn't use F for, let's say, factory. I'll use exclamation mark. So there's a factory that can handle 2, A, B, C. These are the kind of relative positions. A factory that can handle 4, D, E, F. So if I were to test a path where ABC gets repaired at factory 4, then B gets factory 4 because that's kind of the nearest one. But then E would need to go all the way to 2, which should indicate that there's some crossover, which should indicate that there was a mistake done, because then A should definitely have gone to 2 rather than 4. Yeah, I think that logic is fine-ish. Or that, I mean, I'm not that. I think that logic is correct. How to incorporate that into the code? Like you're choosing random. You're choosing for each robot. You choose either the nearest left, or the nearest right hand factory. If there are no right hand factories, that goes to the nearest left hand factory. And if the nearest left hand factory has 0 repairs, then this is just a non-working path. If it's non-working, then how do you trace back? Right? If it's non-working, then you should not have even explored this path up to this point. You should have gone left earlier. Yeah, I mean, minimize. Yeah, I mean, if you'd gone left earlier, would that have left earlier? Would that have somehow been overwritten by going right? So if I gone left earlier for A and B, is it possible that that state doesn't get pushed into the later states, and so therefore I just lose track of it? C, so A, B goes to the first factory. C, D, E, G has to go to the second factory. So keeping track of the smallest one, where index of the robot, position of the nearest left. Maybe so. Index of the robot, position of the nearest left available factory. And direction the last robot went. I guess the position of the left available factory, and also this would need to have the number of repairs done at that factory, because that would differentiate it, right? The state. If there was the nearest available factory is this one, but has 3 versus 4 repairs available, Those are two different states. Okay, and that, I think that means this thing might be wrong. Because the number of available uses of the factories themselves could be a huge number. So that adds like, normally if that was reasonable, then it's something small rather than rather than n for the number of robots. I mean, n here I guess is kind of small too. It's up to 100, right? So maybe that doesn't strictly rule it out. Position the nearest left available factory. And the number of repairs done. Can't do a greedy approach. Can I do a binary search? I don't think I can do a binary search. There's just too many ways of binary search would imply that I could somehow verify a guessed distance. Verify that some input distance to the function, to the kind of the verification function, that it's possible or not possible to have the robots travel a minimum distance that is less than that value to get repaired. Back to the good old heap. Good old heap. Can I somehow store this information with heaps? I'm thinking that somehow it needs to deal with the no crossover facet. Although the no crossover facet again just doesn't solve it. It's just no crossover is necessary but not sufficient. Necessary but not sufficient. For each robot A goes, so A either, so let's say that the positions are just like spaced one apart. A would need to go to factory at 4, so it needs to spend 3, B needs to spend 2, C needs to spend, no, sorry. A needs to spend 1, B needs to spend 2, C needs to spend 1, D needs to spend 1, E needs to spend 2, G needs to spend 3. I wonder. Does the distance matter? I guess the distance do matter. Each factory each factory. Robots go one way, factory goes another way. Robot goes left, next robot goes left, next robot goes right. So it's, okay, let's say the factories were X and Y. And X can do 2, Y can do 4. So how would I think about just solving this mechanically? So it's either A goes to X or A goes to Y. A goes to X costs 1. A goes to X costs 1. X becomes X1. And the cost there is 1. And A goes to Y. Y becomes 3. And the cost there is 3. And then for each of these, if A goes to X, then B goes to X. X becomes 0. Total cost here is 3 because it's 2 plus 1. Or B goes to Y. Technically, do I need to keep track of X still? If B goes rightwards, interesting. If B goes rightwards, C cannot go leftwards because if C goes leftwards, then it would cross over with B. So, so BC needs to either go in both left, both right, or left, right. BC can't go right, left. Okay, I guess is that anything useful? If you have a robot and the next kind of factory or robot is a robot, then those two robots cannot go in opposite directions, or not go in crossing over directions. I don't know if that's useful. I do not know if that is useful. So maybe I should think about it in terms of factories rather than robots, or the factories pick up robots. Maybe the factories. How would the factories think about picking up robots? They would extend the range of robots that they have on the left and right side. Oh my god. Was I really this much better whenever I first solved this thing? Maybe. Maybe. Constant struggle. Heaps. 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 Although it'd be, yeah, it just cannot be linear, right? Like there's no way this is fucking linear. If this was linear, then they would just slam it with a 10 to the 5th number of robots and factories. Although really, if it's linear, then they just go 10 to the 6, and then if this was binary search, they might go 10 to the 5th, to be honest. Or binary search or n log n, some sort of sorting. So maybe this is actually DP. Maybe this is something I need to do. Position of the nearest left factory. The nearest left factory has to have some. The nearest left factory of the current robot. Does that really matter? Position of the nearest left robot. And the nearest left robot the last robot needs to have moved left. Or if the last robot moved right, the nearest left robot needs to be between those two. Yeah, if the last robot moved right, then the next robot has to be moving right or moving left, but there has to be a factory between the two. Alright, this is too late. Alright, I think I'm gonna call this one early.